Dear students, today we will see the crystalline state and the types simple cubic cell, body center cubic and face center cubic, and HCP, that is hexagonal closed pack structure. So before that, I just want to give some idea about what you mean by electronics and the atom. So that will try to understand, make you to understand very easily. So when you see the definition of electronics, so it used to study the flow of electrons or study of control of electrons. So we used to say study of flow and control of electrons. So where, especially in vacuum, gases and semiconductor, with electrons, that is defining your electronics. Now when you, before going to the crystal structure, I just give an idea about atomic structure. You want to know what is you know already this atomic structure, just give some little bit idea about important points about atomic structure. So it was represented like a Bohr model. So the model was based on the Bohr model. So it was actually proposed by Niels Bohr in 1915. See, when you see the atomic structure, the important thing here is you have a proton, that is a nucleus. In nucleus you have proton and neutron. It is a positive charge carriers. We used to say that proton is a positive charge carriers. The outermost you have a n number of cells. You have n number of cells that is defined by the principal quantum number, like a 1, 2, 3, 4 up to 7, n1, n2, like n equal to 1, n equal to 2, n3, 4, 5, 6, 7. So each cell have a subcell, each subcell have an orbital. Each orbital have a 2 electrons. The 2 electrons have opposite spin. One electron will rotate in forward, other will rotate in the backward. Every orbital have 2 electrons. So here the subcells are given with the understanding of S, P, D, F, G, H, etc. So maximum number of electron in any cell, it is given by the formula of 2n square. You know, the n is a principal quantum number. So here you have a subcell, orbital, and the electrons you can see. So S define 1 orbital, and P define 3 orbital, and D define 5 orbital, and F define 7 orbital. Each orbital, as I said, you have a 2 electron. So 3 orbital 6 electron, 1 orbital 2 electron, and 5 orbital 10 electron, 7 orbital 14 electron. So here another thing, the outermost cell have a less attraction because the radius is large with the nucleus. The attraction is very less when you compare with the innermost cell. So outermost cell generally contribute for producing the valency electron. So when you are giving the energy, the electron will be moved from the valency band to the conduction band. So outermost you have a cell. Outermost you have another representation. This is the conduction band. So electron will be moved from the valency band to the conduction band when energy is given, excited. So this is about a atomic structure. Just I given the idea. Okay, now I'll just show you some crystal structure. Maybe it give the real right. See, you can say mold of atom. So it's nothing but a crystal. You have it's a bonding together. It's a representation of crystal. You have a lakhs of like a billions of atoms are tied together. So it is a representation of native copper. It is a pyrite Fe2. It is a quartz, and it is a snow crystal. So these are the few representation of the crystal you can understand, just to have a glimpses of photocrystals. Now let me give the idea of solid state. When you speak about a solid state, generally define the structure, property and synthesis of any solid materials. Generally, the solid materials are, it is classified into two types: crystalline solids and amorphous solids. When you say it is a crystalline solids, the solids are typical geometry. You have a typical geometry, so that generally defines by the arrangement of atom molecules throughout the network. Through the network of the crystal, it is a defined structure in the long range order. Long range order in the sense it's a continuous periodicity. But when you go for amorphous, you don't have any defined structure. You do not have any defined structure. Even like above the temperature, I can mold or I can change the shape. The best example I can say here is glass, rubber, plastic. Above a certain temperature, I can mold or I can anything I can do. So it has the property of rigidity and incompressibility, but to the certain extent. After that, it don't have. So this is the thing about solids, crystalline and amorphous solid. They just give the idea. So when you say, what is the special thing about a crystal? See, the precise point I will say here is, it's like a precise symmetries. It's a complete periodicity. It's a complete long range of order. It have a flat surface. Have straight edges. These are the three unique points about a crystal. When you say what do you mean by crystalline state, the crystalline is a solid, in which the atoms are bound with each other in the regular pattern. You can see here, it is a representation of a copper. It's a face-centric cube actually. It's a face-centric cube representation. You can see it's all are bonded each other. All it's bonded completely, have positive ions and negative ions together. Right, the positive and negative ions are inside this. Right? So it's completely shown here. Right? So the important property in the crystalline state is periodicity. Okay, the periodicity is a very important property of a crystal that you want to understand here, which leads to the term called long range order. So that is with the periodicity, we have a term called long range order. So it is repeated in the equal regular intervals of many times to produce the periodic array of atoms that constitute the crystal structure. See, when you are claiming it is a crystal, you can claim only if you have a property of periodicity. It's a periodic array of points in space. That is a very powerful word you can say here. It's a periodic array of points in space. It's a powerful word to represent the crystalline state. See, when you speak about what do you mean by actual crystal? The crystal is nothing but a sum of lattice and basis. What is a lattice? Lattice is nothing but a periodic array of geometric point in space, infinite. But it don't have any atoms. And environment of any point is identical to that of any other point. You can see here, all are complete periodicity with the equal intervals. That equal interval we used to say A. You can see the difference between the 2 points is A. With the angle of 90 degree you can see here. The angle of 90 degree. This is a complete unit cell. You have n number of unit cell. You have n number of unit cell. Right? You have n number of units. When you speak about what is a basis, the basis is nothing but a identical group of atoms or molecules. The sum of lattice and basis is called crystal. Generally, when you speak about especially in the lattice, you have a lattice vector. The lattice vector gives the idea of both the magnitude and direction. Right? So you can see here the lattice vector is any vector joining two lattice point, right? So here it is very important to understand unit cell. What is a unit cell? The unit cell is a volume, area and the 2D. It is repeated by being translated by the lattice vector. So it is a lattice vector. It is connected with the lattice vector with the complete periodicity. So unit cell is the most convenient small cell in the crystal. It's a convenient small cell in the crystal structure that carries a property of the crystal. It generally carries the property of the crystal. The repetition of unit cell in 3 dimension will generate the whole crystal structure. You have a continuous repetition of unit cell. It's building the concept of whole crystal structure. I hope you understood, right? So it's a very important thing to understand. The repetition of a unit cell in the 3 dimension generates a whole crystal structure, right? So this is the thing you want to understand about a crystal. The crystal is sum of lattice and pieces. Now we will go for some familiar structure. See, you have a n number of lattice type. Actually you have a n number of lattice type. The mathematician, they have classified many times based on the concept of previous lattice. They have different representation of the spaces. Okay, the first we are going to discuss here is simple cubic cell. When you say it's a simple cubic cell, you can see you have 8 corners. You can see 8 atom at the corners. Now you want to find what is the total number of atom in one unit cell. You have a continuous periodicity. Please understand, this is only one cube. You have a lakhs of cube in the crystal. I have taken only cube for your understanding. When you see the single cube, you can see you have a 8 corner with the 8 atoms. So the contribution, the 8 corner, that is NC is a 8. The contribution, each unit cell will be connected with the 8 other nearest atoms, right? The contribution will be 1 by 8. So that means the number of atom in one unit cell will be 1 atom. I hope you getting my point, right? The coordination number is 6. The coordination number generally defined by ligancy. So that is generally defines then the total number of atoms that are central atom, that is central atom or ion hold that is to the nearest neighbor in a crystal. That is defined by the coordination number, also set to the ligancy. When you see here 6, it was given for simple cubic cell. See, very simple. See, you take this unit cell, so you can see the neighbor is, this is our neighbor, and this you have a continuous infinite, right? This connected to the upper layer, and you can see the neighbor also like this, right? So here you have a A, you have another A. So if you count 1, 2, 3, 4, 5, 6, totally you have a 6 neighbor atoms. So coordination number is 6. The preferred example here is polonium dioxide. This has the structure of simple cubic cell. Next we are seeing the body center cubic unit cell. Body center cubic unit cell. Right here you can see I have shown only the one part of the structure. Okay, here I have shown you only the one part of the structure from the crystal. This is a reduced sphere representation. This is a reduced sphere representation for the BCC cell. It's a reduced sphere representation to understand. See the difference between the simple cubic cell and body center cubic cell. Center you have one atom, that is a body center atom. First we will be seeing how many number of atom in the BCC cell. You have 8 corners, each will be sharing, that is a contribute to the 8 other atoms. That is 1 by 8 per corner atom. So 8 into 1 by 8, you have 1 atoms. One body center atom, it is contributing to the another, so to the another body center atom. So that is 1 into 1. It is contribute only 1, right? So no other way. So it may connect to the another body center atom. So 1 into 1, 1 atom. So total number of atom per unit cell is 1 plus 1, 2 atoms. That's it. When you see the coordination number 8, so when you take this unit cell, you can see the neighbor atom. This is 1, this is 2, this is 3, this is 4, right? So similarly here you can see the 5, 6, 7, 8, it was connected. The best example we can say for BCC structure here is the lithium, sodium, potassium, chromium, barium. These are the like a familiar metals which you used in the BCC, which have a structure of BCC. So here what you want to understand here is the number of atom which present in one unit cell is 2 and coordination number is 8. So this is the two things you want to understand in the every structure. The possible metals I have listed in the example, you can see here. So the different, you can see the space is A. The distance between the two is A. It's uniform throughout the all unit cells. So in the crystal, if you take, you have a n number of unit cells. So the third thing is a face center cubic unit cell. The familiar metals for the face cubic center cells are aluminum, copper, nickel, gamma iron, gold and silver. So this is a best structure. It's shown for copper. You can see here. So this is a one part. It's focused here. The you can say diameter of 2r. So this is a reduced structure, reduced pair for the FCC. That is a face center cubic cell. See, when you see the number of atom in the unit cell, 8 corners, no doubt 8 corners. The contribution also will be 1, 1, 2, 3, 4, 5, 6, 7, 8. No doubt you have a contribution of 1 by 8 corner atoms. That is 8 into 1 by 8, 1 atom. Then 6 face center atoms. See, 1, 2, 3, 4, 5, 6. You have a 6, okay, in the 6 phases of the cube. Okay, so I hope you understood, right? 1, 2, 3, 4, 5, 6. Okay, so 6 phases you can see. So there is a face center atom. So each will be contribute of 2. So one on the left side, another on the right side. Each will be connect with the contribution with the other atom will be 2. So 1 by 2. 1 by atom by 2 per atom unit cell. So 3 atoms. So 3 by 2 you have a 3 atoms. So here the 8 corner plus 6 face center atom give the structure of face center cube. Okay, so you can see here, and total atom will be 4. The total number of atom in the unit cell will be 4 atoms. The coordination number is 12. See, when you take here, see this for this unit cell 1, 2, 3, 4. See in below also you have a 1, 2, 3, 4. So that is 2. You can take like a stack of 2 layers. 1, 2, 3. Here you have a 4, here you have a 4, here you have a 4, 4, 8, 12. So that is a coordination number is given as a 12. Okay, so here you have a coordination of 12. Okay, so the center unit cell, it is connected to 4. Above you have a same 4. Below you have another 4. Total 12. Okay. So the next is a hexagonal closed pack structure. So the familiar name for closed pack structure is ABB type. Here it is shown here. The best the metal have a structure of HCB is cadmium, magnesium, titanium, zinc and zirconium. These are the familiar metals that used in the room temperature. See here, its a structure is somewhat different. It is like a complete hexagonal. See, you can see here. So like this, it will be arranged. So complete hexagonal. You can see this is a A type, and this is a B type. You can see this is a A type, and this is a B type. See, this is a layer 6. Above you have a 3, and below also you have a 3, right? See, you have a, if you take one, this is a 6. Above this you have a 3. Below this you have a 3. So 3, 3, 3, you have a 12 coordination number. So the nearest that is founded to the neighbor is 12, right? So I hope you understood, right? So AB is a A and this is a B. Similarly, you have a above also, you have a complete periodicity, right? It is an infinite arrangement of long range of order. You have a continuous lack of layers. So the coordination number will be 12. And if you look at the number of atom in the HCP unit cell is 6. See, first let me take for the corner atoms. So corner atoms you can see 1, 2, 3, 4, 5, 6. So each will be contributed by 6, right? It will be contributed by 6. So 1 by 6, 12 will be having 2. Then if you see the example structure, you have a face centered. Face centered means you have a like a 2. This is 1. This is 1. Okay, so it each have a contribution of 1 by 2. Each have connected with the contribution of 1 by 2. Above 1, below 1. So 1 by 2. So 1 by 2 into 1 by 2, 1 atom. So I hope this you understood. This is a corner atom. This is for face centered atom. You can see is the top and bottom. So that have a contribution of 1 by 2. And body center is 3. So 1, 2, 3. So this is connected completely to the only to this inside to the cell, not away. So you can see here, this is only to the center. It is complete bounded to the structure, not to the outer structure. So contribution will be only 1. So 3 into 1, total number of atoms will be 3. So 3, 2, 1, totally 6. Okay, so this is about a type of different crystal structure. Today I explained you what you mean by atomic structure, the Bohr model, then I have seen the simple cubic structure, then face center cube, body center cube, and the hexagonal closed packed crystal structure with the explanation. Also we have seen what is the coordination number and what is the total number of atom in unit cell. I hope you understood.